So 9-4 is about testing the difference between proportions. So in our previous ones, we talked about our independent variables and our dependent variables and the difference of means, and now we're doing the difference between proportions. So in proportions. All right, and so just like we had in our previous chapters, like chapter 7 and chapter 8 when this was first introduced, we're going to be sort of doing the same idea as what we've been doing. You know, we've always worked with the formula of, you know, our test value being whatever we observed, okay, like our sample. And let me actually move this down a little bit so it doesn't interfere. Test value is going to equal what we observed, so whatever we saw in our sample, minus whatever we expected, which is from our population, over our standard error. And so really every single one of our formulas that we've learned has followed this format. So the same thing applies with our proportions. And our formula that we'll be using the z-table, first off. So that's our test value. It's going to come from the z-table. And it should be our p sub 1 or p hat sub 1 minus our p hat sub 2 minus p sub 1 minus p sub 2, all of that over our standard error, which is going to say the square root of p bar times q bar times the quantity of 1 over n plus 1, n sub 1, plus 1 over n sub 2. So there's a lot of things happening here that I'll go ahead and explain. The first thing is that obviously this right here, that first little section, is again our sample information. Okay, this is our sample proportion. All right, and then again we have our population, or not really our population, but we have our population proportion over here, and again we're not going to know what this is, and so typically this population proportion will not be given to us, and therefore is going to equal 0. The bells are still working at the school. How fun. All right, so after that, we can get into our standard error down here. And really, I'm just going to focus on this piece right here. This p bar and this q bar, really just the p bar, so just ignore that. So here we have the p bar. The reason why we're using our p bar is because if we were to just use our standard error from our previous chapters, in the previous chapters we had sort of all of our information and we could just plug it into the formula and be done. But now, because we're working with the sample proportion and we don't have the population proportion, this p bar is a way for us to consider all of the data, okay, that we have. And in the previous formulas, it would be just focusing on p sub 1, or the first proportion, or it might just be focusing on the second proportion. But if you're just focusing on one thing and not both things, you don't have the whole picture of your data, okay? And so in order to compensate for that and to consider the whole data, we are going to use a formula for this p bar. P bar is going to equal x sub 1 plus x sub 2 over n plus 1 plus n sub 2. All right, and of course q bar is just the complement of p, so it would be 1 minus p bar. But so here we have our two variables, and remember these two variables are supposed to be like 8 out of 12 people love going to the movies, or whatever it may be. That 8, that would be our variable, our first variable. And then you might compare that to 6 out of 25 people like going to the beach. So then we would add the 8 and the 6 together up here. So we can say 8 and then 6. All right, so those are our variables from our data pieces. Okay, so this is our formula that we're going to use. So let's go ahead and use it with an example. So here's our first example. It says 12 out of 34 small nursing homes had a resident vaccination rate of less than 80%, while 17 out of 24 large nursing homes had a vaccination rate of less than 80%. At alpha equals 0.05, test the claim that there is no difference in the proportion of the small and large nursing homes. So our 12 out of 34, this right here, is our first piece of information that gives us, what we need to find our p-hat. And remember, p-hat is our probability from the first sample, or really p-hat sub 1 is the probability of our first sample. So we can say that our p-hat sub 1 is going to equal to 12 out of 34, which is going to be 30 or 0.35. I was going to say 35%, but it means the same thing. All right, and so then we have our next piece, 17 out of 24. That's going to be our p-hat sub 2, and that's 17 out of 24. And if I type that in the calculator, I'm going to get 0.71. So I have my two probabilities, and I can plug them into this parenthetical statement in a second. I'll do that 1 second. I'm trying to go in order as I read it, and then I'll follow my 5 steps to doing the hypotheses and then finding the critical value. So hold on. From my reading, from my little example, I don't really have anything else going on, so I can go ahead and start working on my steps. So first things first, I'm going to go ahead and write my hypotheses. My null hypothesis is when my two probabilities are going to be equal. Okay, and remember, when we're doing this, we are taking our sample data and we're trying to make conclusions about the population, which is why in my hypotheses I'm not considering the sample proportion. I am considering the population proportion. So my hypotheses is going to be p sub 1 equals p sub 2, and then that means the alternative, and I don't see anything about like it being less than or greater than. I mean, I do have this less than right here, but it's talking about the vaccination rate. It's not really talking about my proportions. So I'm going to go ahead and say that my alternative is when they do not equal. And another reason why I don't think it's a less than symbol here is because in the last sentence, which is typically where we look to find, whatever keyword we're looking for, at alpha equals 0.05, test the claim that there is no difference in the proportion of the small or large nursing home. In that last sentence, I don't have any less than or equal to or less than or greater than words. All right, so my alternative is going to be when it's not equal, and then it's asking me to find or to test the claim that there is no difference. Okay, if there is no difference, that means they're equal. So now my my null hypothesis is going to be my claim, which is different. Typically it's our alternative, but that's all right. If we were to make our little box, we can cross out, I'm so used to doing those. We can cross out all of the alternative statements, and now we're just left with the null. All right, so I found my hypotheses. The next thing I need to do is find my critical values. Remember, critical values are based off of alpha. Alpha equals 0.05, and it is a two-tail test, so I can take that and divide it by 2, and I should get 0.025. If I go to my z-table, I need to find this value. All right, so here is my z-table from our forms document. I see this 0.0250 right here on my z-table, and I can see it hits at negative 1.96. And remember, since it's two-tailed, it's going to be positive or negative, so now I'll go back and I'll write that. So my critical value is going to be positive or negative 1.96. All right, so if I were to sort of draw my picture, and I'll draw my picture right down here, I have positive 1.96 and I have negative 1.96. Remember, we draw our picture with our critical values. Oops, forgot the 6 there. And anything beyond that critical value, either if where the tails are, that's where you're going to shade. All right, so the last thing I need to do is find my test value. Test value is based on the formula, which I wrote at the very top. I wanted to make sure that we sort of had that in our mind as we were doing this, and I can go ahead and start plugging certain things in. I got z equals our sample proportions, which we already found was 0.35, minus 0.71. And then we said that the population, we don't know, so it's going to be 0. So I'm going to ignore it for now. And then now I can go down to the very bottom, and I can plug in the other pieces I know. Now, in order to find the p-bar, the p-bar is going to be something slightly different. So I'm going to change my color really fast, and I'm just going to calculate the p-bar. Remember, p-bar is when you take your two variables and you add them together over your two samples. Oh my. Right, as I was saying, over the first sample size plus the second sample size. So I can come up here and I see it's 12 out of 34, so 12 out of 34, and I'm going to add that together with my 17 out of 24, and this is going to give me 29 out of 58 with a decimal of 0.50. All right, so that makes my Q bar pretty easy because it's 1 minus 0.5, which is going to be 0.5 again. So I can go back and fill that into my denominator, 0.5 times 0.5 times 1 over 34 plus 1 over 24. And now I can just use my calculator and type everything in. All right, so here's my calculator. I typed everything in, pressed enter, and I should get an answer of negative 2.70. And I'm going to round to 2 decimal places because that's where my critical value is. All right, so this is going to equal negative 2.70. And then I'm going to put that on my picture so I can see it clearly, negative 2.70. And I have to ask myself, is that less than or greater than negative 1.96? It is less than, so it needs to go to the left, negative 2.70. And I have decided that since it's in the shaded region, I need to reject my claim. So if I were to do my little box where I crossed out my stuff, I would say it is this top left-hand statement, which should read as, there is enough evidence, and I don't really have room at the bottom, so I'm going to write it at the top. There is enough evidence to reject the claim. The claim being that there is no difference in the proportions. There is, apparently. We have evidence to support that there is. All right, so that is our answer for that. So let's go ahead and do one more example along these lines. It'll be slightly different. I just want to make sure we are really just getting used to it. So let's go to that next one. All right, so a study finds that in a random sample of 50 burglaries, 16% of the criminals were arrested, and in a sample of 50 car thefts, 12% of criminals were arrested. At alpha equals 0.01, can it be concluded that the percentages of people who commit burglaries and were arrested are more than the percentages of people who commit car thefts and were arrested? All right, so we have our percent already right off the bat, so that's nice. Later on, we're going to have to do something with that, but for now, we are good to go. I'm going to start off with my hypotheses. The first one has to be when the proportions are equivalent. Alternative, it comes from the last sentence. Can it be concluded that percentages of people who commit burglaries and were arrested is more than the percentages of those who commit car thefts? So again, when you're doing this, you need to go in order. We start off with our burglaries, and we compare them to our car thefts, all right? And they're saying that the burglaries is greater than, so I'm going to make the mouth face the burglaries because that makes it makes that side bigger. All right, so when I write this, I'm going to say P1 is greater than P sub 2. Okay, and remember, you need to make sure you do it this way just so that in case they switch things on you, sometimes it shows itself as a lesson symbol. So I just want to make sure when you're doing this, you're being very careful and you can get your answer. All right, so next thing we need to is find our critical value. We have our alpha equals 0.01. It is a one-tail, so I do not need to divide it. So I'm going to go to my z-score. Remember, you're using a z-table, as in Z, for this proportions. So let's go to that and find 0.01. All right, so here is our z-table. We have our pointer or our cursor on our 0.01, and really it says 0.0099, but this is going to round to 0.01. We could go one up, but that is actually sort of, I guess you could say 2 away, and this one's only 1 away. So that's why we're going to pick this one, because it is closer. And that's going to give us a negative 2.33. Negative 2.33. So let's go ahead and write that. Negative 2.33. And really, because it is on the right-hand side, remember we know it's on the right-hand side because our greater than symbol is pointing to the right, we know that we're actually only dealing with positive numbers. So really, this is not going to be a negative 2.33, it's going to be a positive. And the reason why we're able to conclude it's positive is because, remember, this is based off of a symmetrical distribution. So what's true on the left-hand side is true on the right-hand side as well. You just have to make sure that if it's on the left, it is a negative, but if it's on the right, it is a positive. And in this case, we used the information on the left to get the answer, which is why it was negative, but our information is not really on the left, it's on the right. And so that's why we have to make it positive. So now we have our critical value, and we can find our test value next. So this should say, not t, z equals our p hat sub 1 minus p hat sub 2 minus p sub 1 minus p sub 2, all of that over our standard error, which is the square root of p bar times q bar times the quantity of 1 over n sub 1 plus 1 over n sub 2. And now we can start plugging things in. We have our 0.16 minus 0.12. We don't have any information about our population. So now we need to go down to the p-bar. Now, the p-bar is going to be a little bit different this time because, remember, in order to find the p-bar, we need to have the variable added to the sample sizes, or divided by the sample sizes, 1 plus n2. All right, so if we go over here, it doesn't tell us how many people there are to get the 16%. They just tell us that in the bottom we have 50 people in our sample for the burglaries and 50 people in our sample for the car thefts. Okay, so we have those two pieces of information, but we don't actually have the exact number of people, but that's okay. We can actually still figure it out. If we have 16% of 50 people, it's very simple. All you have to do is we have to multiply 16% and 50 together, and we'll get an answer. So all you need to do is type into your calculator 0.16 times 50. Okay, so 0.16 times 50. Okay, and if you do that, you should get an answer of 8. Okay, so that's the first one. We can do the same thing with the next piece, the 12% of 50 car thieves. So that'll be 0.12 times 50, and that is going to equal 6. Okay, so now we do have the exact amount, 8 plus 6. And if you're ever like a little concerned as to, is this really true or not, remember that you can just do 8 over 50, type that into your calculator, 8 divided by 50, and you should end up with 0.16. So it does actually work out, okay? And I'm just showing you that what you found is true. All right, so we can get rid of that, and we can continue on. 8 plus 6 is going to give me 14 over 100. Therefore, my p-bar is 0.14, and my q-bar is the complement of that, 1 minus 0.14, which is going to equal 0.86. All right, now that I have all of that, I can go back to my calculations up here, and I can plug all that in. I'm going to make it a little bit smaller. All right, so here are my pieces of information. I just made it a little bit smaller so that I could have enough room. This is going to be 0.14 times 0.86 times 1 over 50 plus 1 over 50. Plug it into my calculator and we can get an answer really quick. All right, so I plugged it into my calculator. I can move my cursor over if I really want to. It doesn't really matter. Press enter and I get a test value of 0.5. And I'm going to round to 2 decimal places, so it'd be 5/8. Okay, so my answer will be 0.58. Now that I have that, I can go ahead and draw my picture. It's a terrible little curve, but all right. Here we go. Our critical value is on the right-hand side. It's 2.33. All right, I shade in my tail. I take my test value and I put it over here somewhere. It's close to 0, so I'm going to put it over here, 0.58. It is in the non-critical region, so I'm going to say we do not reject it. We do not reject it. Therefore, we're going to circle this answer, and our answer should be there is not enough evidence. Not enough evidence to support the claim. To support the claim. All right, so I went ahead and showed you those 2 different ways to do it. Again, it's the same formula each time. Make sure you're using your P bar down here for your denominator. It's the only way you can get your answer. Remember, we use the P bar because if you look at just one sample piece's information, it's not going to tell you the whole picture. So that's why we have to consider both, which is why we add the 2. All right, so the next little section is doing critical values, or not critical value, but confidence intervals with the same pieces of information. So I'm actually going to transfer some of that information down and we'll get started. All right, so for confidence intervals, the formula is a little bit different. Our formula is going to be the p hat sub 1 minus our p hat sub 2 plus or minus our z sub alpha divided by 2 times it's not the standard error, it's actually a little bit different. It's going to be p hat sub 1 times q hat sub 1 over our sample size, our first sample size, plus p hat sub 2 times q hat sub 2 over our second sample size. All right, so I went ahead and wrote our critical values and our test values for our for example 1, because it's saying find the 95% confidence interval from example 1. I went ahead and wrote all of that so that we can use it. We might not use this critical value because remember, in our critical value for our first problem here, our alpha was, oh no, actually it is the same alpha. Alpha is 0.05, so that will work out. It was a 2-tailed test, if you remembered. Our alternative was p sub 1 does not equal p sub 2, so we've already divided it. So we will, in fact, use this critical value. That may or may not work in the next one. All right, so we have this piece, which is going to go right down here in our z. And then we have our other pieces for our p hat sub 1 and p hat sub 2. So we're just going to go ahead and start plugging things in. This part matches these. All right, so I'm going to plug all that in. It'll say 0.35 minus 0.71 plus or minus 1.96 times the square root of, and p hat sub 1, that's going to be 0.35. And then remember, q is just the complement, right? So our complement of our first proportion is going to be 0.65. 1 minus 0.35 is 0.65 over our sample size was 34 plus 0.71 times 0.29, all of that over 24. All right, so these pieces of information we just plug in from our from our problem, okay? The only thing that we have to calculate is that 0.65 and that 0.29. And remember, we did that by finding the complement. 1 minus 0.35 is 0.65, and 1 minus 0.71 is 0.29. All right, so we went ahead and did that. We can take our calculator and figure this out. So here I have everything typed in. I'm going to press enter, and I get my first value at negative 0.602. I'm going to do the same thing again, but change it to a plus sign. So I'm just going to press second and then enter. That repeats everything verbatim onto my calculator, but I'm just going to change this symbol right here to a plus sign. And that'll give me negative 0.118 if I round to 2 decimal places. So I'm going to go back and type that in. Negative 0.602, and it would be P1 minus P2 as my variable at negative 0.118. All right, and so because 0 is not in between my two values, all right, remember, if 0 is in between your two values, then you are going to keep your claim. But if 0 is not part of it, then you are going to reject the claim. So since 0 is not in my interval, I reject the claim. And remember, the confidence intervals are just used to help us have another route to decide are we keeping or are we rejecting our claim. So since 0 is not part of my interval, I'm going to reject the claim. All right, so same idea for the next one. All right, so again, they want to find the 95% confidence interval from example 2. And so in our example 2, our alpha was actually 0.01. And so our critical value is not going to work this time. We have to find our new critical value. So this is going to require a little bit of work. I'm going to do it off to the side. We have our alpha is equal to 0.05 because it's a 95% confidence interval. Remember, you have to divide it by 2 because that's what the formula tells us to do. And so this is going to be 0.25. And really, this is going to be positive or negative 1.96 again because we actually did this work for example 1, so I don't have to redo it again. All right, so I just wanted to show that to you really quickly. And now I'm going to go ahead and start plugging things in. I have my p hat sub 1, that's 0.16, minus my p hat sub 2, which is 0.12. Remember, I got that from this piece right here, plus or minus 1.96. Again, we had to find that new critical value because of our alpha changing values. And sometimes it happens, so please don't think that, like, if it does happen, you've done something wrong. That's not the case. Times the square root of, okay, this is going to be 0.16, and to find the complement of that, or the q, it's 1 minus 0.16, which is going to give us 0.84, all of that over 50, plus 0.12 times the complement of that, 1 minus 0.12, which is going to give us 0.88, all of that over 50. And now I just plug it into my calculator. All right, so I typed it in, press enter, and we get negative 0.096. I can do this again with a plus sign in front of my 1.96 instead of a minus sign, so give me a second. Plus, and I get 0.176. So I can go ahead and write that. All right, so negative 0.096 P1 minus P2, that's the variable we use, 0.176. And this time, 0 is actually in between these two things, so we would not reject. Don't reject, because 0 is within our interval. Okay, and that makes sense because in example 2, we had a test value of 0.58 and we did not reject. So we ended up with the same answer that we had in example 2. So just showing you again, when you're doing this, it's just an alternative way to get your answer, and hope that helps, and good luck on your homework. Please make sure you are sending me a message on Teams if you have any questions.